So before I get started, we should talk about significant figures. So what do I mean by significant figures? If you're looking at significant figures here, one of the things that you see here is that you see that I have 3 here, I have 3 here, and I have 3 here. So when you look at that, you're going like, okay, that looks like 3 significant figures, but then you come over to this one, you go like, whoa, that's 1 sig fig. Well, we get lazy here. And what we really mean when we say 60 degrees, we believe that this is a perfect 60 degrees. So that means we come in here and we're really talking as many zeros as you want. So it's not a 1 sig fig problem. In this case, it's a 3 sig fig problems. And I know that some of you get bent out of shape on some of this stuff, but we're among friends. And that's pretty much the standard. If I write 1 or if I write 100, does that mean 100 is really 1 significant figure? The answer is no. A number that we write like that, we typically means that it's a perfect 100. Okay, let's go. So now that I've said that, one of the things that we want to do here is that we want to go in and we want to start looking at this example, the next example. So let's read this together. So remember, there's 2 pictures that I'm going to draw. I'm going to draw the physical picture, and then we're going to go in and draw the mathematical picture. And at some point, we're just going to stop drawing the physical picture, and we're going to go directly to the mathematical picture. Okay, and that's the way that you'll see that we'll be doing in chapter 5 and 6, especially then. Okay, so here we go. I'm going to set up again my coordinate system. What's my coordinate system? I have the north, east, south, west axes as before. So I'm going to draw them here in a minute. So, but the first picture that I'm going to draw here so that I can conceptualize what's going on, I'm going to draw the so-called physical picture. If I'm looking at my physical picture, what do I see here? The first thing here, it says that a hiker, let me move this up a little bit higher. A hiker undergoes 3 successive displacements as follows. There's 4 kilometers in the southwest. So here I go. So I'm going to try to even these guys out. So I got 3. So I'm going to go something like this. So when I look at this, of course, this is my north, east, south, west. So southwest literally means what? It means that it's at 45 degrees in the southwest direction. So there's equal parts here. Now note it says 4. So let's say that this is what this guy looks like right here. And because this is the first step, I'm going to go in here and I'm going to call this the A vector. And then it says that you're going to take a 5 kilometer in the east direction. So my guess here, I'm going to just kind of guess. I think this vector should be longer than the red one. So let's say I do it like this. So here's my second step, my B. And then I'm going to go 60 degrees northeast by 6 kilometers. So then I'm going to come in here and I'm going to go what? So what I'm going to do here is that I'm going to come in here and I'm going to just set up a little tiny coordinate system. If this is 45 degrees right there, then I'm going to have a longer vector. And I'm going to say that this angle right here, from here to here, is 60 degrees. And this is my vector C. So the resultant from the origin then is going to be this other vector, which I'm then going to label in black. Should I do that in black? How about if I do that in violet? So then I'm going to come in here and I'm going to just say, okay, so this is my resultant vector right here. And this is then going to be A plus B plus C, which I'll continue to call D. So my whole goal is to calculate the magnitude of D and calculate the angle of D. But like I said before, this is not a good picture. What we want is we want the mathematical picture. So if I go and I look at my mathematical picture here, what I'm going to do then is that I'm going to do the exact same thing as I did before. I take my red vector and I'm going to move it at, let's say, something like this. There's my A vector. And then I'm going to take my B vector. I'm going to put its tail right here. And then I'm going to take my C vector and I'm going to put its tail right up here. And ooh, I could see that I'm going to run out of space. So I'm going to move this down just a little bit here. And so if I look at this guy here, my blue vector is going to be at 60 degrees. So it's going to be, let's say, something like this, and it's going to look like that. And so there's my C vector. So then if I use the parallelogram rule, here I go. Parallelogram rule says what? I'm going to go down to here. I'm going to go this way. And then I have a resultant vector right there. So if I go down to here, here's my vector A plus B. And then I'm going to add A plus B to C here. So then that means here that I got to do something like this. And then this guy is going to go something like this. And of course, these are all rough sketches here. And what you're seeing here is that parallelogram rule tells me that I'm going to get what? A vector that looks something like this. And if we had scaled these all exactly right, these two vectors would be the same, exactly the same. So that's how we want to do that. And the only thing we know is we know what? We know that this angle right here is 45 degrees. And we know this blue angle here is 60 degrees. So here we go. Let's go do it. So what we want to do here is that we now have to convert vectors that have magnitude and direction into components. So our job here is that we need to convert vectors with magnitude / direction into components. And then what we do then is that means that we're then going to do what? We're going to have, that means we're starting with the magnitude, we're starting with an angle, and then I need to make them into components. So I get AX equals A cosine of theta, AY equals A sine of theta. And once I get the X's and the Y's, what you're going to see here is that then when I form the vector D, I'm now going to have A plus B plus C, which means, of course, that I have dx, dy. And when I have these, this really means AX, BX, CX, and then the same for the Y's. That's what I got to get. So let's go focus on each of the vectors here. So we're going to start off with the vector A. Okay, so here we go. So the vector A, when you look at this thing here, what's it look like? Well, we know that the vector A has a magnitude of what? 4 kilometers. And we know that this angle is 45 degrees. So it's important here that typically most people believe that if you say the x component, you really mean that the angles, and you say the word cosine, then that means that the angle is always measured relative to what? The x-axis. Whether it's the negative x-axis or the positive x-axis, doesn't matter. And so what we said before here is that how you measure the angle depends on how you look at the world. So let's go do this here. So what we want to do here is that we're then going to start with what? So we start, right? We start with A equal to 4 kilometers, and theta, because it's measured relative to the negative x-axis, I'm going to put in quotes here 45 degrees. And you'll see why I'm saying that. So I'm going from here to there. So let's go look at this thing here. So the traditional way is to do what? The traditional way is to go in and measure the angle relative to the x-axis. So if we measure, so how about if we do it slightly different? So now we're going to do case number 1. We measure angle relative to positive x-axis. So what does this tell us here? Well, if you look at this thing, there's an angle of 180 degrees right there. So that means here that the angle of A should be 45 plus 180, which should give you 225 degrees. So if I do that, we know that that's the angle that we're going to get. So let's go calculate this thing here. So if I know, go calculate AX, that means I'm going to get A cosine of what? 225. Why am I writing cosine? Because I'm measuring it relative to the x-axis. And so when I plug this in, I'm going to get what? 4.0 kilometers times cosine of 225. And the number that I get here is minus 2.83 kilometers. And then I do the exact same thing for AY. But this time, of course, it's the sine. And if I calculate that number, I'm going to get 4.0 kilometers sine of 225. And of course, I'm going to get the exact same value because we know that sine and cosine are the same for the same angle. So what you're seeing here is that you're getting what? Well, what you're seeing here is that you're getting two pieces of information. Note that you get the minus sign. So the minus sign is telling you about what? Direction. And note that you're getting these values right here. These values are telling you the magnitude of the components. In other words, what that 2.83 is telling you is the length. So the angle, of course, only tells you the direction. So there's another way that we can do this without ever using the 180 degrees. And this brings us to case 2. Here, what we're going to do here is that instead of measuring from the positive x-axis, we're going to measure the angle relative to minus x-axis. But this time, we're going to sort of like put in our thinking cap to think our way through here. So when I look at this picture here, what we do here is that at first, we ignore the minus in the minus 45 degree, excuse me, ooh, I think I have to step back. What I did here is that I did not state what I wanted to state. Sorry about that. I'm going to go back and I'm going to erase this. Okay. My apologies. So what we're going to do here is that we're going to recognize that we're measuring from the negative x-axis, right? So we first recognize that we measure from the negative x-axis. So this tells us here is that we focus only on the magnitudes. And then what we do is that we come back, and by hand add the proper direction. And what I mean by that here is that, note, we went in and we added the 180 degrees, and I'm saying you don't have to do that. So what we do then is that we want to come in and then we say, what's the length of AX and AY? Well, the length of AX, in other words, when I look at this guy, the length of AX is really A cosine of 45. And if I punch in my numbers in here, I then going to get 4.0 kilometers cosine of 45. And that gives me, of course, 2.83 kilometers. So now what do we do? By hand, we say, which quadrant is that x component looking at? And we come back here and we say, well, if I look at the quadrant, we can see that we are in the third quadrant. And in the third quadrant, we know that the x component must be negative. So then we come in and we go like, oh, really? If I now add the sign to it, I then say AX, of course it's 2.83, but that's just the length. But because it's in the third quadrant, we put in the minus sign. So this tells us that it points into the third quadrant. And then I do the same thing with the AY. I come in and I go, I want the length of this guy, which of course is then going to be 4.0 kilometers. And I know that we get the same one, but I think we should go through the process. And what am I going to get? 2.83 kilometers. And then I come in by hand, and what do? I add the sign, and we could see that AY points negative. So then AY, of course, is 2.83 kilometers. And then I come in and I go, that's in the third quadrant. So then we say the same type of thing. Now note, look at the answers. Negative 2.83, negative 2.83, negative 2.83, negative 2.83. I get the exact same answer, but the only thing I'm doing is that I'm paying attention which quadrant. When we calculate using the angle 45, we are literally only calculating the magnitude. Okay, so that's for vector A. Let's go to vector B. So here I go. So if I look at vector B, well, we saw that vector B lies along the x-axis. So we immediately conclude here that by is 0 since the length of B, since it's always there, we could see here that this guy is that amount. So we don't have to do anything on this guy. So we just come in here and just say, okay, what's the magnitude of B? Not the magnitude, but the vector B has to be this. So this guy has to be what? 5 kilometers. That guy has to be 0. So then we're set. So we got B. So then I move on. Let's go to C. So if I go to vector C here, what do I see here? Well, we have the same type of thinking as before. We have a vector that's what? 60 degrees measured, and that where the length of C was 6 kilometers. And of course, we could see that this is measured relative to the x-axis. So here we go. So we start with C. It has a length of that, and it has an angle of this. And now we want to convert it into Cx, which will be C cosine of 60, and Cy, which would be C sine of 60. So if I do that, I'm just going to keep plugging in my values. This will be 6 kilometers cosine of 60. And because it's in the first quadrant, my length here is 3. But because I see it's in the first quadrant, I give it a sign of plus because we know that's the case. If I repeat this for this guy, what's the length of this guy in the first quadrant? It's 5.2 kilometers. But because we know it's in the first quadrant, we have that. So now we have all of our components, right? We have our C's, we have our B's, and we have our A's. So now I'm going to go form the vector D. So if I go form the vector D, I'm then going to do what here? So here we go. So now I want the magnitude. I want the, oops. The vector D is this now. So I know that D is of course A plus B plus C. And we know that this guy should be AX, BX, CX, and then of course these other components. So now I'm just going to start putting them in. So what do I know here? I know that this vector, so if I go in, I know that this guy is going to be minus 2.83, and I know that the A is minus 2.83. We just calculated that, right? Here's my A's. Now I'm going to look at B. You can see that B is 5 kilometers and 0. So then this guy should be 5, and this guy should be 0. Then I'm looking at C now, and you can see that this guy is going to be 3, and this guy is going to be 5.2. So if I compute this, I'm going to get a value of what? Well, you can see this is 8, roughly 3, so it should be a little over 5. So then I'm going to get positive 5.17. And then my next one, you could see that I'm still going to get a positive value. So it should be roughly half of that. So then I'm going to get positive 2.37. And so this is my vector D now. So now that I have D, I could then go calculate its magnitude and its direction. Here we go. So the magnitude and direction are, here we go. So the magnitude of D is then going to be dx squared plus dy squared square root. So if I plug this in here, I'm going to get 5.17 squared plus 2.37 squared square root. And the length that I get here is 5.69 kilometers. And that's the magnitude of D. Let's go get the angle now. The angle theta is the tan inverse of dy over dx. So if I plug those numbers in, I'm going to get the tangent inverse. And now look at the signs here. The signs tells us what? That it should be in what quadrant? The first quadrant. So I know I should have a plus sign there. So when I look at my value, then it's got to be 2.37. Then I look at the x value, and I know that that guy must be in the first quadrant. So I see that plus sign. So when I look at the angle, I know that it should be a vector in the first quadrant. So when I calculate this guy, I get value of 24.6 degrees for theta of D. So you can see here that I now have this. So is this realistic? Well, we know that that angle is in the fourth quadrant, the first quadrant. So when I come up to my picture up here, we can see that D is in that thing. Now, I know that this isn't drawn to scale or anything, but it looks like the angle is less than 45 degrees. And that's a good thing because it looks like we are calculating an angle less than 45 degrees.